Dear friends, welcome to yet another session for software engineering. In today's session, we will be discussing more about how art transformed into engineering, and we will also look into the requirement for software engineering principles. So moving ahead, the early programmers used exploratory style of programming, which is also known as build and fix style. It is basically the software development practice of a novice who has just started to program or has learned programming and are doing small assignments. So basically, these programmers used their intuition in order to build their programs because there were no such other defined techniques. In this style, as soon as the problem statement is given, based on the understanding, the programmer starts writing the program. And initially, a dirty program is quickly developed. Now, what is a dirty program? A dirty program is that kind of a program which is developed using intuition and not focusing much upon the bugs. And basically, these dirty programs, they have a lot of errors and bugs built into it. As you document this development style of build and fix in the form of maybe a schematic diagram, you will see that initially the coding part is done and then it is tested until there they can find out all the bugs, and once these bugs are found out, they start fixing these bugs one by one and again go for the testing phase and repeat this process until and unless they finally get the required code they need to deliver. This model of an exploratory style of development, as you proceed, you will contrast this basic style of development with engineering style of development. As most of the new programmers use this to develop small programs, so exploratory style of programming or build and fix style of programming was a huge success in the initial days where the size of the programs were small. But what happened that this exploratory style was replaced? The very first point that we can discuss is it can be successfully used for very small programs only. So basically we call them as maybe a toy program where there are minimum lines of code involved and the programmers can use their basic intuition in order to write down those lines of code. If you look into this graph, this is basically a graph which represents the effort, time and cost that is invested in programming a software or in programming or writing down a particular program as compared to its program size. Understanding the plot, as the program size increases, you develop large and larger programs and still keep using the exploratory style or the build and fix style. You will see that for small programs it is successful, but as the program size increases, the effort, time, cost all increase exponentially. That means maybe to develop a 100-line program, it took couple of hours, but to develop a 1,000-line program, it might take several months or it might culminate into a year. But after some size, the exploratory style just breaks down. Even if you try your best using the exploratory style, still you cannot develop after a certain size. But this does not happen when you use software engineering approaches. There is almost a linear increase in the effort, time and cost as compared to the program size when you consider the software engineering graph that I'm talking about, the blue line in the graph. So if a 1,000 lines program took couple of hours, then a 10,000 line program will take only about 10 times of that and not 100 times or 1,000 times as compared to your exploratory style of programming. However, if you deploy a machine with all the software engineering principles and methods, then it will give you exactly a linear rise, which is represented using the green line. On the very basic thing you need to remember is that in the exploratory style, the cost, effort, time increases almost exponentially, whereas using software engineering principles, it's down to almost a linear increase. The second important point is generally exploratory style results in an unmaintainable code, and it is quite difficult to use this style in a team development environment because your intuition, it might be different from your team members' intuition. So based on such wide variety of intuitions, it will be almost next to impossible to deploy your own ideas in one particular program or one particular software. Now the basic question arises is, why does the effort required to develop a product grow exponentially with the product size? Or why does the approach completely breaks down when the product size becomes large? So, in order to answer these two questions, we need to understand a very important concept related to human cognition. So, how does this human cognition mechanism work? It is a very fundamental principle. The long back results from Miller 1956 said that the human memory can be made up of two distinct parts. One is known as short-term memory and the other is the long-term memory. And in the former one, which is in the short-term memory, is one where you remember something for only a small duration of time, that is, it might be for several seconds or just minutes, whereas in long-term memory it will be for months and years. So the question is, this is a basic example. If the question is, if it is 10 a.m. now, how many hours are remaining today? And how will your memory respond to this? The way the human mind will work is, the 10 a.m., the first part, which is 10 a.m., it is in the short-term memory, and from your long-term memory you will fix the duration of one day, which is 24 hours. Then there will be a mental manipulation unit where you will compute the difference 24 minus 10, which is 14 hours or 13 hours and 15 minutes, 50 minutes approximately. So basically, when a small, even for such a simple question like how many hours are remaining if it is 10 a.m. now, both your short-term memory and long-term memory is put into use. If you analyze this in a schematic diagram, you will see something like this, where in your processing center, initially the short-term memory is triggered first, and the short-term memory triggers the long-term memory in order to respond to a particular question. So basically, both of these memory sections are put into use. And an item is stored in the short-term memory. An item might be a set of related, it is generally a set of related information. It might be digits or words or different types of pictures. So anything which are related information, they form items. So an item basically, which is situated in a short-term memory, it can get lost either due to the decay with time or displacement by newer information. Decay with time as in, like, if you are supposed to remember this for a few seconds, maybe that period has passed, so the information might be lost, or it might be so that instead of that particular information, a new information is replaced. The main thing is that it stays for very short time, and depending on new information coming, The time duration also can be very short, typically for tens of seconds. But someone can remember it longer by recycling the memory. And generally, let's consider the recycling part. What do you mean by recycling the short-term memory? For example, you went to the market and wanted to buy a few things, and just you can keep on recollecting it again and again. So even though things should be there for for around some seconds or some minutes, it might last in your short-term memory for around 1 or 2 hours, because you are constantly repeating it and your memory is refreshed and recycled as long as your particular requirement is completed. So each item normally occupies one place in the memory. But if you can relate these different items together, which is also known as chunking process, so it will become relatively easier in terms of the space or in terms of the memory that is being put into use. The information that should normally occupy several places when it was independently stored now will use only one place of memory if we can chunk the related information together. So the conclusion is that if you are remembering something and you are able to build the relation between the things that you want to remember, then it becomes rather easier. And this entire process is known as chunking. Considering an example for chunking, so if you are asked to remember the number which is displayed on the slide, which is 11010101. So this is a binary number. You will struggle to remember this because it's a long string and there are too many digits, and then the relation among them is also not very obvious. But then if you group this into 3 in the octal form, which is around 6251, it becomes easier to remember. This is because of the limitation of human cognition mechanism that the short-term memory can hold up to 7 items. Now this is a very interesting concept, the magical number 7. As long as you're able to build relations, it becomes easier for remembering till it is less than 7. This is an established fact that the human cognition system can easily remember things which is up to a length of 7, which is also known as your chunking principle. So, if a person deals with 7 or less number of items, the understandability is easier. However, if the information increases, it becomes exceedingly difficult to understand and most importantly to retain them in your memory. This can be directly applied in your program development. For example, if your program is having just a few variables, it is easily within the grasp of an individual, right? It's easier to understand, it's easier to manipulate, and it's easier to implement. Now, if the number of independent variables in the program increases, it becomes exponential. It quickly exceeds the grasping power of an individual and requires an unduly large effort to master the problem, which might lead into your program crashes as well. To understand a program, you must look at the variables as how do they interact. If the number of independent variables in a program is small, it becomes easy to understand. But as the number of variables increases, that is, if the number of independent variable is more than 7 according to your human cognition mechanism, then it's a large problem which will deal with many things. So it becomes difficult. Now the question is, how does the software engineering principle contain the complexity of this problem? Now, for a human mind, it is difficult to remember things beyond 7. So instead of a human being, if a machine with software engineering principles could be used in order to generate the program or find out the solution, you will find that the slope of the curve will be linear as it was shown in your graph, the green line. Then why does this effort size curve become almost linear when these principles are deployed? It becomes linear and overcomes all the problems of exploratory as well as your software engineering principles because it tries to overcome the human cognitive limitations using certain techniques and principles. These two techniques, abstraction and decomposition, are put to use so that the curve gets linear, so that it overcomes the issues that was related to your human cognitive systems. These two major techniques are used to overcome the cognitive limitation of 7, the number 7. So these two important principles are used in almost every technique. If we have to understand these two fundamental techniques to handle which handles the complexity, we have to take two different examples. So first, we will understand what abstraction exactly is, and then finally we'll go to decomposition. Now, when we are talking about abstraction, in abstraction we focus our attention only on some aspect of the problem and ignore the rest or the other aspects or the irrelevant details. This is also known as model building. Now, let us consider an example that you want to develop a large building and see how does it look. So you will ignore all the other aspects like strength, wall thickness or the internal plan, etc. And you will concentrate only on its frontal appearance and ignore everything to construct a model of the frontal view of the building. Similarly, for the floor plan of the building, you will just concentrate on that and don't bother about how does it appear externally, the thickness of the wall, etc. Concentrating on hitting requirement of a room, you will just look at where it is located or how much heat it is generating, etc. and you will omit other unimportant aspects. So for every problem, we can construct an abstraction. This abstraction is also called as model building, and if you create a model, you concentrate on some aspect and ignore the rest. So this is known as abstraction, and it is a very important technique in software engineering, as you will need to build models of everything, that is requirements, design code, and this is probably the only way to tackle the complexity. The next example you can take is if you are asked to develop the overall understanding of a country. So generally, in order to find out where is which are the directions or whatever, where are the residential complexes located or where are the schools located, you generally do not need to go from house to house or door to door in order to find out the locations. We can simply refer to the various maps of that country. So we can have to ignore the other references or other irrelevant information in order to find out our requirements and strictly stick to our goal. A map, in fact, is an abstract representation of a country itself. So to continue with this, we will finally move to the next important principle, which is decomposition. Now, decomposition, as you already know, it is basically to break down a problem into many smaller independent parts and then take up each of the problem one by one and solve it separately. What is the need of breaking it down? So that each of the part could be easily understood and could be deployed and fixed as and when required. And after that, we can simply integrate all the parts and give the final output. If you take the example of a book, generally if it is in the form of chapters, it becomes easier for you to understand the concepts rather than mixing up the whole syllabus together. So these two important aspects forms the basis of software engineering principles and how they actually overcome the human cognitive mechanism, and thereby making the graph linear for the effort and time as compared to the program, effort, time and cost as compared to the program size. So using these principles, using these two concepts, however large your program might be, it becomes almost a linear curve or just a linear curve to solve the entire problem. So thank you. We'll see you in the next session.